Okay, this is the first video I'm going to make on waves, and it's where we're just going to have a little bit of a talk on what this wave's about. Don't underestimate waves. It's a small topic, but it's usually the one that students do the worst in, because I think they underestimate it. So what did we learn in Year 12? Well, we did do some waves. We did stuff like diffraction. We did a little bit on that, which was good. We may even have looked at the diffraction formula a little bit. We looked at lenses and mirrors, which was where we did the ray diagrams, and we had Newton's formula, Huygens formula. Huygens especially important for looking at diffraction. It was those sort of questions. Diffraction involved a lot of looking at interference, and from year 11 we'd already looked at a wave. What was a wave? A wave was mainly a transfer of energy, and we saw that there were two different types. Well, there's more than two different types, but we looked at longitudinal and transverse. We found that longitudinal, the particles vibrate parallel to the direction of energy transfer. With a transverse, the particles oscillate transverse or perpendicular to the direction of energy transfer. We talked about electromagnetic waves, electromagnetic radiation, EMR. We know that light is a form of electromagnetic wave, infrared, microwaves, X-rays, gamma rays, all the rest of it. So this is what we've learned so far, this sort of stuff. Now, a wave is a transfer of energy. That's the primary thing you've got to remember about waves. They have a velocity depending on their medium, depending on the density of their medium, and depending on the tension or the forces involved in the medium. So what I'd like to show you first is just a little video, not a little video, but a little mathematical expression. That's the formula we usually use for waves when we get to university, but we don't use this one here, which I think is a bit of a shame. It's got two independent variables, x and t. So this is not something you can plot just on the normal xy axis. What you would have to do is decide whether you're going to plot the x or the t as your independent variable, and the other one could be constant. So at a constant position, x equals x naught, then this expression would be fixed at a single place over a period of time. So if you had your wave looking like that, this is at a constant place. Whereas if you put t at a certain t, we get the same thing, but we'd have x as our independent variable, whereas we had t up there. So basically the thing with waves is they change in space and they change in time. So if you stick your time and see what happens at this particular place, you'll see changes in the amplitude over time. If you stick in a certain time, you'll see changes in space. It's like stopping time, this one, and you went, okay, what happens 2 millimeters from here, 5 millimeters from here? So that's a mathematical way of looking at the wave. Two things to this little formula are this here, omega, is the omega we've come up with a few times, and that's related to the frequency. I think we all know that omega equals 2 pi f, right? This one is radians per second, whereas this is just wavelengths per second, and a wavelength has 2 pi radians in it. So that's the frequency component here, whereas the wavelength, k, relates to wavelength. K is called wave number, and it is the number of radians per meter. So if you divide 2 pi by the actual wavelengths, what you're going to get is radians per meter. All right. So we all know about wavelengths. A light wave, like green or something, is 500 nanometers is the wavelength. Very, very small. Half a micron. Now, half a micron means that there would be 2 million of them in 1 meter. So 2 million times 2 pi. 2 pi is about 6. We're talking about 13, 14 million radians per meter. That's a pretty big K. Whereas a radio wave might have 100 meters for its wavelength. So how many radians does it do in a meter? Well, 1/100th of 2 pi. So this is the terminology for the maths of waves, but we don't really need to know much about that. But it's quite simple. What we are going to learn about here is there are a few different areas. We're going to look at just normal combining of waves. We're going to look at something called beats. That's when you combine waves of different frequencies, slightly different, and you get a beating. Explaining that is hard. You need to learn how to explain that. We're going to look at standing waves, very important. We need to be able to explain what a standing wave is and how they are formed. And we will look at the musical instruments with regard to that. We'll look at tubes and strings. That's part of standing waves. We're going to look at something called Doppler. That's the whole car coming towards you, or the siren or something, or a train, and it gives you that increasing tone as it comes towards you, then a sudden decreasing tone as it zooms away. So we need to look at the Doppler equation to know how to do that. And the last part of this unit is interference, mainly with regard to something called diffraction. We're going to look at Young's slits, which we looked at in year 12, but we didn't look at the formula. And we're going to look at the diffraction grating. Two mathematical formulas that we need to know about. There's a mathematical formula for Doppler. There's a very simple one for beats. So there's a little bit of maths there. Standing waves, it's some mathematical formulas for working out the instruments and drawing them. Doppler, there's a mathematical formula and a mathematical formula there. So we've got 1, 2, 3, 4, probably 5 or 6 new formulas in this unit. All right, that's enough for an intro.